10-volt reading between the neutral and earth bar in a panel within a telecommunication shelter can stem from several factors. Firstly, improper neutral-ground bonding at the transformer can be a significant cause. If the neutral and ground are not correctly bonded at the transformer, it can lead to a voltage drop between the 2 points at the shelter. The reason for this is that neutral current may then return through the ground path, creating a potential difference. Secondly, uneven load distribution across the 3 phases can also contribute to this voltage difference. If the 3 phases are not balanced in terms of load, the neutral conductor carries the unbalanced current. This unbalanced current flow creates a potential drop along the neutral conductor, resulting in a voltage difference between the neutral and the earth bar. Thirdly, the presence of harmonics in the electrical system can be a factor. Nonlinear loads such as rectifiers and inverters, which are common in telecommunication equipment, generate harmonics. These harmonics can circulate through the neutral ground path, leading to voltage distortion and a potential difference between the neutral and earth. Fourthly, a seemingly simple cause could be measurement error. Before delving into complex explanations, verify that the digital multimeter, or DMM, being used is properly calibrated and that the test leads are correctly connected. A 10-volt reading could simply be a result of a measurement error if the testing conditions are not ideal. Fifthly, the resistance of the earth-ground connection itself plays a crucial role. High earth resistance can cause a voltage drop between the neutral and earth bar. It's essential to ensure that the earth-ground connection has a low resistance path to ground. Sixthly, ground loops within the system can also lead to voltage differences. If multiple ground paths exist, they can create ground loops. These loops allow current to flow through the neutral ground path, again causing voltage differences. Seventhly, induced voltage from external electromagnetic fields can also contribute to the problem. If the telecommunication shelter is located near strong electromagnetic fields, these fields can induce voltage in the neutral ground path. This induced voltage can contribute to the observed difference between neutral and earth. To mitigate these issues, several steps can be taken. Firstly, ensure proper neutral ground bonding at the transformer. This is a fundamental requirement for a stable and safe electrical system. Secondly, balance the loads on the 3 phases as much as possible. Distributing the load evenly reduces the neutral current and minimizes voltage drops. Thirdly, minimize harmonics in the system. This can be achieved using filters or isolation transformers to reduce harmonic distortion. Fourthly, verify the accuracy of the digital multimeter measurements. Always use calibrated equipment and proper testing procedures. Fifthly, ensure a low earth resistance. Test the earth-ground connection and ensure that it meets the required standards. Sixthly, eliminate ground loops. Review the grounding system and eliminate any unintended ground paths. Seventhly, investigate potential sources of induced voltage and consider shielding or other mitigation measures if necessary. Non-technical things to consider are safety, adherence to electrical codes, professional assistance. Safety should always be a top priority when dealing with electrical systems. Before performing any tests or making any changes, ensure that the power is disconnected and that appropriate safety precautions are taken. Electrical codes and regulations should be adhered to. All work should be performed in accordance with the applicable electrical codes and regulations. These codes are in place to ensure safety and prevent electrical hazards. If unsure about any aspect of the electrical system, consider seeking professional assistance. A qualified electrician or electrical engineer can diagnose the problem and recommend appropriate solutions. Additional technical considerations include neutral conductor sizing. Ensure that the neutral conductor is adequately sized to handle the maximum unbalanced load. An undersized neutral conductor can cause excessive voltage drop. Furthermore, surge protection should be reviewed. Install surge protection devices to protect sensitive telecommunications equipment from voltage surges and transients. Also, review the grounding system design. Ensure that the grounding system is properly designed and installed to minimize ground impedance and prevent ground loops. Equipment grounding is also important. Make sure that all equipment is properly grounded to provide a low impedance path for fault currents. Finally, perform regular inspections. Regularly inspect the electrical system to identify and address any potential problems before they become serious. Other things to consider are understanding three-phase power, harmonics mitigation techniques, grounding system design, and troubleshooting techniques. In three-phase power, there are generally three conductors, each carrying an alternating current that is offset by 120 degrees in phase from the other two. This arrangement provides a more stable and efficient power supply compared to single-phase power. However, it also requires careful balancing of loads across the three phases to minimize neutral current and voltage imbalances. Techniques to mitigate harmonics are important because harmonics are caused by nonlinear loads, such as electronic devices and power supplies, which draw current in a non-sinusoidal manner. These harmonic currents can distort the voltage waveform and cause problems such as overheating of equipment, increased energy losses, and interference with communication systems. Harmonic filters, such as passive filters and active filters, can be used to reduce harmonic distortion. The grounding system design is an important aspect of electrical safety. A well-designed grounding system provides a low impedance path for fault currents, which helps to protect people and equipment from electrical shock and damage. The grounding system should be designed to meet the requirements of the applicable electrical codes and standards. Techniques to troubleshoot involve systematically identifying and resolving problems in electrical systems. Common troubleshooting techniques include visual inspection, voltage and current measurements, and continuity testing. A digital multimeter, or DMM, is an essential tool for troubleshooting electrical problems. Common electrical code requirements must also be adhered to. Electrical codes, such as the National Electrical Code, NEC, in the United States, provide detailed requirements for the installation and maintenance of electrical systems. These codes are designed to ensure safety and prevent electrical hazards. It is important to be familiar with the applicable electrical codes and to follow them carefully when working on electrical systems. It is important to understand the concept of impedance. Impedance is the total opposition to current flow in an alternating current circuit. It includes both resistance and reactance, where reactance is the opposition to current flow due to capacitance and inductance. High impedance in the grounding system can limit the flow of fault current, increasing the risk of electric shock and equipment damage. It is also important to understand bonding versus grounding. Bonding refers to the connection of non-current carrying metal parts to create an electrically conductive path. Grounding, on the other hand, refers to the connection of the electrical system to the earth. Bonding is essential for providing a low impedance path for fault currents, while grounding provides a reference point for the electrical system and helps to stabilize voltage. It is important to use the appropriate test equipment. When troubleshooting electrical problems, it is important to use the appropriate test equipment. A digital multimeter (DMM) is essential for measuring voltage, current, and resistance. Other useful test equipment includes an insulation resistance tester, a ground resistance tester, and a harmonic analyzer. Insulation resistance testing is used to measure the resistance of the insulation surrounding electrical conductors. Low insulation resistance can indicate damaged insulation, which can increase the risk of electric shock. Ground resistance testing is used to measure the resistance of the earth-ground connection. High ground resistance can limit the flow of fault current, increasing the risk of electric shock and equipment damage. A harmonic analyzer is used to measure the level of harmonic distortion in an electrical system. High levels of harmonic distortion can cause problems such as overheating of equipment and interference with communication systems. It is also important to understand the different types of grounding systems. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common types of grounding systems include the grounded system, the ungrounded system, and the impedance grounded system. In a grounded system, the neutral point of the electrical system is connected to the earth. This provides a low impedance path for fault currents and helps to stabilize voltage. In an ungrounded system, the neutral point of the electrical system is not connected to the earth. This can reduce the risk of electric shock, but it also makes it more difficult to detect ground faults. In an impedance grounded system, The neutral point of the electrical system is connected to the earth through an impedance, such as a resistor or reactor. This limits the flow of fault current and helps to protect equipment from damage. It is also important to understand the different types of ground electrodes. A ground electrode is a conductive object that is buried in the earth and used to connect the electrical system to the earth. The most common types of ground electrodes include ground rods, ground plates, and underground metallic water pipes. Ground rods are typically made of copper or galvanized steel and are driven into the earth. Ground plates are typically made of copper and are buried in the earth. Underground metallic water pipes can be used as ground electrodes if they are electrically continuous and in direct contact with the earth for at least 10 feet. When installing ground electrodes, it is important to follow the requirements of the applicable electrical codes and standards. The location and depth of the ground electrode should be chosen to ensure that it is in contact with moist soil and that it is protected from damage. Also consider the role of transient voltage surge suppressors or TVSS. Transient voltage surge suppressors, or TVSSs, are devices that are designed to protect electrical equipment from voltage surges and transients. Voltage surges can be caused by lightning strikes, switching operations, and other events. TVSSs work by diverting the surge current to ground, protecting the equipment from damage. It is important to select TVSSs that are appropriate for the specific application and to install them in accordance with the manufacturer's instructions. Also, review the specific telecommunications equipment. Telecommunications equipment can be particularly sensitive to voltage fluctuations and harmonic distortion. It is important to ensure that the electrical system is properly designed and maintained to provide a stable and clean power supply for the telecommunications equipment. It may be necessary to install special filters or isolation transformers to protect the telecommunications equipment from electrical noise. Consider using power quality monitoring equipment. Power quality monitoring equipment can be used to continuously monitor the electrical system and to detect any problems such as voltage fluctuations, harmonic distortion, and ground faults. This equipment can provide valuable information for troubleshooting electrical problems and for preventing equipment damage. Proper documentation is also important. Keep accurate records of all electrical work, including the installation of ground electrodes, the testing of insulation resistance, and the measurement of ground resistance. This documentation can be helpful for troubleshooting electrical problems and for demonstrating compliance with electrical codes and standards. Proper earthing helps ensure safety in electrical installations by providing a low impedance path for fault currents, minimizing the risk of electric shock, and stabilizing voltage. A 10-volt reading between neutral and earth could be a result of one or more of the reasons discussed. It is important to systematically investigate each possibility and take appropriate corrective actions to ensure a safe and reliable electrical system. Grounding systems must adhere to regional and local electrical code standards. The grounding electrode conductor connects the neutral bus or the equipment grounding bus to the grounding electrode. It is essential for carrying fault current back to the source. Sizing is based on the size of the service entrance conductors as per NEC Table 250.66. Grounding electrode types include metal underground water pipe, metal frame of the building, concrete tin-cased electrode, ground ring, and rod and pipe electrodes. The grounding electrode must be suitable for the soil conditions and meet code requirements for size and installation. The equipment grounding conductor, or EG, connects the non-current carrying metal parts of equipment to the grounding system. It provides a path for fault current to return to the source, tripping the overcurrent protection device. Sizing of the EGC is based on the rating of the overcurrent protection device protecting the circuit as per NEC Table 250.122. Types of EGC include wire, conduit, and other approved metal raceways. Ground fault circuit interrupters, or GFCIs, are designed to protect personnel from electrical shock. They detect small imbalances in current between the hot and neutral conductors and trip the circuit, cutting off the power. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Surge protective devices, or SBDs, protect electrical equipment from voltage surges caused by lightning, switching operations, or other disturbances. SBD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SBD should be installed at the service entrance and at any point where sensitive equipment is connected to the electrical system. Bonding refers to the connection of non-current carrying metal parts to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding is required for metal water pipes, gas pipes, and other metal objects that could become energized. Separately derived systems, or SDS, are electrical systems that receive power from a source other than the utility grid, such as a generator or transformer. SDS must be grounded separately from the main electrical system. The grounding requirements for SDS are outlined in NEC section 250.30. Resistance to ground is the resistance of the earth-ground connection. Low resistance to ground is essential for providing a low impedance path for fault current. Resistance to ground should be measured using a ground resistance tester. The NEC requires that the resistance to ground not exceed 25 ohms for a single rod electrode. Voltage drop is the decrease in voltage that occurs along a conductor due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction or fail. Voltage drop should be calculated for all circuits to ensure that it does not exceed the maximum allowable limit, typically 3% for branch circuits and 5% for feeders. Harmonic distortion is the distortion of the voltage and current waveforms caused by nonlinear loads such as electronic devices and power supplies. Harmonic distortion can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with communication systems. Harmonic filters can be used to reduce harmonic distortion. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and harmonic distortion. Poor power quality can cause a variety of problems, including equipment malfunction, data loss, and increased energy costs. Power quality monitoring equipment can be used to identify and address power quality problems. Electrical safety audits are comprehensive assessments of an electrical system to identify potential safety hazards. Electrical safety audits should be conducted regularly by qualified professionals. The audit should include a visual inspection of the electrical system, testing of electrical equipment, and a review of electrical safety procedures. Electrical safety training is essential for all personnel who work with or around electrical equipment. Electrical safety training should cover topics such as electrical hazards, safe work practices, and the use of personal protective equipment. Electrical safety procedures are written procedures that outline the steps to be taken to ensure electrical safety. Electrical safety procedures should be developed for all electrical tasks, such as working on energized equipment, performing lockout-tagout, and responding to electrical emergencies. Personal protective equipment, or PPE, is equipment that is worn to protect personnel from electrical hazards. PPE includes items such as rubber gloves, insulated tools, and arc flash suits. PPE should be selected based on the specific hazards present and should be used in accordance with electrical safety procedures. Lockout-tagout, or LOTO, is a procedure that is used to prevent accidental energization of electrical equipment during maintenance or repair. LOTO involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. Arc flash is a dangerous electrical explosion that can occur when a short circuit occurs in the air. Arc flash can cause severe burns, blindness, and even death. Arc flash hazard should be assessed before working on or near energized electrical equipment. Arc flash protection includes wearing arc flash suits and using insulated tools. The National Fire Protection Association, NFPA 70E, is a standard that provides guidance on electrical safety in the workplace. NFPA 70E covers topics such as arc flash hazards, electrical safety procedures, and personal protective equipment. Qualified electrical worker is a person who has the skills and knowledge necessary to safely work on electrical equipment. Qualified electrical workers should have completed electrical safety training and should be familiar with electrical codes and standards. Unqualified person is a person who does not have the skills and knowledge necessary to safely work on electrical equipment. Unqualified person should not be allowed to work on or near energized electrical equipment. Working on energized equipment is generally prohibited unless it is absolutely necessary and can only be performed by qualified electrical workers who have received specific training and are using appropriate PPE. Safe work practices are procedures that are designed to minimize the risk of electrical shock and other electrical hazards. Safe work practices include using insulated tools, keeping a safe distance from energized equipment, and wearing appropriate PPE. Electrical emergencies can include electrical shocks, fires, and explosions. Electrical emergencies should be responded to immediately by qualified personnel. The first step in responding to an electrical emergency is to disconnect the power source. The next step is to provide first aid to any injured persons. Finally, the incident should be reported to the appropriate authorities. Remember to always consult the most current version of the NEC and other applicable codes and standards for specific requirements.